Till now, we have discussed three problems based on signal flow graphs. Now, in this presentation, we are going to discuss problem number 4 on signal flow graphs. So, let's get started. Consider the signal flow graph in the below figure. One signal flow graph is given to us, and we need to calculate the transfer functions C1 over R1, C2 over R2, C2 over R1, and C1 over R2. This is the given signal flow graph, and we can see that it is a multiple input, multiple output system, and there are four possible transfer functions C1 over R1, C2 over R2, C2 over R1, and C1 over R2. And we need to calculate all the four possible transfer functions. This is a very conceptual and good problem, so I want you all to watch this lecture very carefully. So moving on to the solution, we know that this is a multiple input, multiple output system, and there are two inputs R1 and R2, R1 and R2, and two outputs C1 and C2, C1 and C2. And we know that if we have more than one input and more than one output, we analyze the systems by using the superposition theorem. That is, when we consider one output and one input, we will assume that all the other inputs and the outputs are 0. In this signal flow graph, there are two inputs and two outputs, and that's why the possible transfer functions are C1 over R1, keeping R2 and C2 equal to 0, C2 over R2, keeping R1 and C1 equal to 0, C2 over R1, keeping R2 and C1 equal to 0, and C1 over R2, keeping R1 and C2 equal to 0. And we need to calculate all the four possible transfer functions in this problem. So let us start with the calculation of transfer function C1 over R1, keeping R2, C2 equal to 0. Moving on to the calculation of transfer function C1 over R1, let us consider the signal flow graph which is given in the problem, and we know we have two inputs R1, R2 and two outputs C1, C2. In this case, we need to find out the transfer function C1 over R1, and that's why we will assume that the input R2 and the output C2 are 0. Now, I want you all to observe this signal flow graph carefully and identify the forward path. We need to start from the input R1 and move till the output node C1. Yes, if we start from this node R1 and we move towards this node X, then if we move towards this node Y, then moving towards this node Z, and finally if we move towards this output node, then this will be the forward path. So the forward path of this signal flow graph will be R1, X, Y, Z, C1. Is there any other forward path in this signal flow graph? No, there is no other way by which we can start from this node R1 and move towards this node C1. And that's why we have only one forward path. Moreover, if we observe this signal flow graph carefully, we can see that this signal R1 is not moving towards this lower part of signal flow graph. That is, there is no effect of this input R1 to this lower portion of SFG. Therefore, this portion of signal flow graph is redundant while calculating C1 over R1. And that's why the effective signal flow graph will look like this when we are interested in the calculation of C1 over R1. Now, let us apply the Mason's gain rule in this signal flow graph in order to calculate C1 over R1. We already know the forward path in this signal flow graph, which is R1, X, Y, Z, C1. And the gain of this forward path will be the product of these four branches, which is equal to 1 multiplied with 2 multiplied with 1 multiplied with 1, which is equal to 2. Now, we will move on to the identification of individual loops. If we observe this signal flow graph, we have two different loops. The first loop is X, Y, X, and the second loop is Y, Z, Y. Now, moving on to the calculation of loop gain. The loop gain of this first loop x, y, x will be the product of these two branches, which is equal to 2 multiplied with minus 1, which is equal to minus 2. And the loop gain of second loop y, z, y will be equal to the product of these two branches, which will be equal to 1 multiplied with minus 2, which is equal to minus 2. Now we will move on to the calculation of determinant of SFG. And we know that delta equal to 1 minus of sum of gains of all the individual loops plus sum of products of gains of all possible combinations of two non-touching loops. But we can see that in this SFG there are no non-touching loops. That is, the number of non-touching loops is equal to 0. And that's why the gains of non-touching loops is equal to 0. Now, if we put the values of L1 and L2 in this equation, we will have delta equal to 1 minus of minus 2 minus 2. The values of L1 and L2 is equal to minus 2. Now, if we solve this, we will have the value of determinant of SFG equal to 5. In this way, we are done with the calculation of determinant of SFG. We will now move on to the calculation of associated path factor. And we know that if we want to calculate the associated path factor, we have to erase or eliminate the forward path. In this signal flow graph, the forward path is R1, X, Y, Z, C1. And if we erase this forward path, the signal flow graph will look like this. Now, observe this signal flow graph carefully and check for the remaining loops. We can see that the number of isolated loops is equal to 0. Because there are no remaining loops as all the nodes are destroyed. So we can say that the associated path factor with respect to this forward path is equal to 1. Because we know that if the number of isolated loops for a particular path is equal to 0, then the associated path factor with respect to that path is equal to 1. Now we are done with the calculation of forward path gain, the loop gain, the determinant of SFG, and the associated path factor. We will now apply the Mason's gain formula in order to calculate the overall transfer function C1 over R1. So we have C1 over R1 equal to summation from k equal to 1 to n pk multiplied with del k over delta. The number of forward paths in this signal flow graph is equal to 1, and that's why the value of n is equal to 1. Now, if we open this summation, we will have C1 over R1 equal to P1 multiplied with del 1 over delta. Now putting all the values in this equation, we will have C1 over R1 equal to 2 multiplied with 1 over 5. The value of forward path gain P1 is equal to 2. The value of associated path factor delta 1 is equal to 1. And the value of determinant of SFG delta is equal to 5. Solving this, we will have the overall transfer function C1 over R1 equal to 2 over 5. And this is the first transfer function, which is C1 over R1, keeping C2 and R2 equal to 0. We will now move on to the calculation of second transfer function, which is C2 over R2. Moving on to the calculation of transfer function C2 over R2, let us consider the given signal flow graph, and we have to calculate the transfer function C2 over R2. We will now assume the input R1 and the output C1 equal to 0. Now, if we observe the signal flow graph, we can see that the input R2 is moving towards this upper portion of signal flow graph. And that's why we will consider this complete signal flow graph while calculating the transfer function C2 over R2. As this input R2 has an effect in this upper portion of signal flow graph too. So moving on to the identification of forward path, if we start from this node R2 and move towards this node P, then if we move towards this node R, then finally if we move towards this node C2, then this will be the forward path. And if we observe this signal flow graph, there is no other forward path in this signal flow graph. So the forward path for the calculation of transfer function C2 over R2 will be R2 P Q R C2. And the gain of this forward path will be the product of these four branches, which is equal to 1 multiplied with 1 multiplied with 2 multiplied with 1, which is equal to 2. Moving on to the identification of individual loops and the calculation of loop gain. So observe the signal flow graph carefully and tell me the number of loops. The first loop will be P, Q, R, P. And the loop gain of this loop will be the product of these three branches, which is equal to minus 2. Moving on, the second loop is x, y, x. And the gain of this loop will be 2 multiplied with -1, which is equal to -2. Now, the third loop is y, z, y. And the gain of this loop is the product of these two branches, which is equal to -2. In this way, we are done with the identification of individual loops and the calculation of loop gains. Now, we will observe this signal flow graph and check for the non-touching loops. We can see that this loop L1 do not have any node as common with this loop XYX, which is loop L2, and this loop YZY, which is the loop L3. So we can say that we have two pairs of non-touching loops. The first pair is L1, L2, and the second pair is L1, L3. Now observe this signal flow graph again and check for three non-touching loops. Yes, the number of three non-touching loops is equal to 0 because we do not have any triplet of non-touching loops. Now we will move on to the calculation of determinant of SFG. And for this signal flow graph, the determinant of SFG delta will be equal to 1 minus sum of all individual loops L1, L2, L3 plus sum of products of gains of all possible combinations of two non-touching loops. And in this signal flow graph, we have two pairs of non-touching loops, which are L1 and L2 and L1 and L3. So we have sum of products of all possible combinations of two non-touching loops minus of sum of products of all possible combinations of three non-touching loops. But we do not have any triplet of three non-touching loops, and that's why the gain of three non-touching loops will be equal to 0. And hence all the other factors will be equal to 0. Now, if we put all the values in this equation, we will have 1 minus of -2, -2, -2 plus product of L1 and L2 will be equal to -2 multiplied with -2, which is equal to 4, plus product of L1 and L3 will be -2 multiplied with -2, which is equal to 4. And in this way, the value of determinant of SFG will be equal to 15. Now, we will move on to the calculation of associated path factor. And we know that if we want to calculate associated path factor, we have to erase the forward path. In this signal flow graph, we have one forward path, which is R2, P, Q, R, C2. And if we erase this forward path, the signal flow graph will look like this. Now, observe this signal flow graph and check for the remaining loops. Is this a complete loop? No, this is not a complete loop, but these two loops are complete loops as all the branches and nodes of these loops are sustained. They are not destroyed. So we have two isolated loops with respect to this forward path. Now, moving on to the calculation of associated path factor del1, which is equal to 1 minus of sum of all the individual isolated loop gains plus sum of products of gains of all possible combinations of two non-touching isolated loops and so on. But in this case, we do not have two non-touching isolated loops. We have two isolated loops, but these are touching loops. And that's why the number of two isolated non-touching loops is equal to 0. And hence, the gain is also equal to 0. Now, if we put the values of these two loop gains, we will have 1 minus of -2, -2. We can see that the gain of loop L2 is equal to -2 and the gain of loop L3 is equal to -2. We have named these loops as L2 asterisk and L3 asterisk as these are special loops because they are isolated loops. Now, if we solve this equation, we will have the associated path factor del1 equal to 5. So now we are done with the calculation of forward path gain, the loop gain, the determinant of SFG, and the associated path factor. We will now put all these values in the Mason's gain formula in order to calculate the transfer function C2 over R2, which is equal to summation from k equal to 1 to n pk multiplied with del k over delta. In this signal flow graph too, we have only one forward path, and that's why the value of n is equal to 1. Now, if we open this summation, we will have C2 over R2 equal to P1 multiplied with del1 over delta. Now putting all the values, we will have C2 over R2 equal to 2 multiplied with 5 over 15. And solving this, we will have C2 over R2 equal to 2 over 3. In this way, we are done with the calculation of second transfer function, which is equal to C2 over R2. We will now move on to the calculation of transfer function C2 over R1. Moving on to the calculation of C2 over R1, let us consider the given signal flow graph one more time. And in this case, we need to find out the transfer function C2 over R1. And that's why we will assume the input R2 and this output C1 equal to 0. Now observe this signal flow graph carefully and check for the forward path. We can see that this input R1 is in the upper portion of SFG and this output C2 is in the lower portion of SFG. And there are two branches which are connecting the upper portion and the lower portion. But we can see that the direction of this arrow is from Q to X. Similarly, the direction of this arrow is from Q to Z. So we can say that the signals in these two branches are moving from this lower portion of SFG to this upper portion of SFG. And that's why there is no way by which we can move from this input node R1 towards this output node C2. And that's why we can say that there is no effect of input R1 into the output C2, because there is no forward path from the input R1 to the output C2. And since there is no forward path, the forward path gain will be equal to 0. And if the forward path gain is equal to 0, then if we apply the Mason's gain formula, we will get the overall transfer function C2 over R1 equal to 0. So the transfer function C2 over R1 will be equal to 0. Let us now move on to the calculation of fourth transfer function C1 over R2. Now moving on to the calculation of C1 over R2. Consider the signal flow graph one more time, and in this case we need to find out the transfer function C1 over R2. And that's why we will assume the input R1 and the output C2 equal to 0. Now let us start with the identification of forward paths and the calculation of forward path gain. And for that sake, we need to start from the input node R2 and move towards the output node C1. So if we start from this input node R2 and move towards this node P, then if we move towards this node Q, now if we take this branch to move towards this node Z, and then finally if we move towards this node C1, then this will be the first forward path. So the first forward path is R2, P, Q, Z, C1. And the gain of this forward path will be the product of these four branches, which is equal to 1 multiplied with 1 multiplied with 4 multiplied with 1, which is equal to 4. There is one more way by which we can start from this input node and move towards this output node C1. If we start from this input node R2 and move towards the node P, then if we move towards this node Q, now if we take this branch to move towards the node X, then we move towards this node Y. After that, we will move towards this node Z, and then finally we will move towards this node C1. So this is the second forward path, which is R2, P, Q, X, Y, Z, C1. And the gain of this forward path will be the product of these branches, which is equal to 1 multiplied with 1 multiplied with 3 multiplied with 2 multiplied with 1 multiplied with 1, which is equal to 6. In this way, we are done with the identification of forward paths and the calculation of forward path gain. We will now move on to the identification of loops and the calculation of loop gain. And we already know that we have three different loops. The first loop is P, Q, R, P, having gain -2. The second loop is X, Y, X, having gain -2. And the third loop is Y, Z, Y, having gain -2. And out of these, loops L1, L2 and L1, L3 are pairs of non-touching loops. So when we apply the formula to calculate the determinant of SFG, we will have the determinant of SFG delta equal to 15. This is the same value that we got in case 2 when we were calculating the transfer function C2 over R2. Because the SFG in both the cases is same. So we can say that if the signal flow graph is same, then the value of delta is the same. We can note one important point here, that the determinant of SFG is unique for a signal flow graph. If we do not change the signal flow graph, the value of determinant of SFG will not change. So the value of delta in this case will be equal to 15. Now we will move on to the calculation of associated path factor. Now moving on to the calculation of associated path factors, and we know the number of associated path factors is equal to the number of forward paths. And in this signal flow graph we have two different forward paths, and that's why we will have two different associated path factors. So firstly we will calculate del 1, which is the associated path factor with respect to the first forward path. So let us consider the signal flow graph, and in this signal flow graph the first forward path was R2, P, Q, Z, C1. And we know that if we want to calculate the associated path factor with respect to this forward path, we need to erase this forward path. So if we erase this forward path, the signal flow graph will look like this. Now observe this signal flow graph and check for the remaining loops. We can see that this loop is not complete as this node is destroyed. This loop is also not complete as this node is also destroyed. But this loop x, y, x is a complete loop as all the nodes and all the branches are sustained. So we can say that this loop L2, which is x, y, x, is an isolated loop, and we will call it as L2 asterisk. And the gain of this loop is -2, which is the product of these two branches. Now moving on to the calculation of del 1, which is equal to 1 minus of individual isolated loop gains plus sum of products of gains of all possible combinations of two non-touching isolated loops and so on. But in this case we have only one isolated loop, and that's why we do not have any non-touching isolated loops. And hence the gain of all the non-touching isolated loops will be equal to 0. Now if we put the value of L2 asterisk, we will have the value of del 1 equal to 1 minus of -2, which is equal to 3. So in this way we are done with the calculation of associated path factor with respect to first forward path. We will now move on to the calculation of del 2, which is the associated path factor with respect to second forward path. So let us consider the SFG one more time, and we know that the second forward path in this signal flow graph is R2, P, Q, X, Y, Z, C1. And we know that if we want to calculate the associated path factor with respect to this forward path, then we need to erase this forward path. And if we erase this forward path, the signal flow graph will look like this. Now observe this signal flow graph carefully and check for the remaining loops. Yes, you are right. The number of isolated loops in this case is equal to 0. As we can see that this is an incomplete loop because this node is destroyed. These two nodes are also incomplete because all the nodes are destroyed. So we can say that the number of remaining loops is equal to 0, and that's why the number of isolated loops is equal to 0. And we know that if the number of isolated loops is equal to 0 while erasing a forward path, then the associated path factor with respect to that forward path is equal to 1. So in this way, we are now done with the calculation of forward path gain P1, which is equal to 4, the associated path factor with respect to first forward path, which is equal to 3, the second forward path gain P2, which is equal to 6, the associated path factor with respect to second forward path, which is equal to 1, and the determinant of SFG, which is equal to 15. We will now put all these values in the Mason's gain formula in order to calculate the transfer function C1 over R2. So we have C1 over R2 equal to summation from k equal to 1 to n pk multiplied with del k over delta. Since the number of forward paths in this signal flow graph is equal to 2, that's why the value of n in this equation is equal to 2. Now, if we open this summation, we will have C1 over R2 equal to P1 multiplied with del 1 plus P2 multiplied with del 2 over delta. Now, putting all these values in this equation, we will have C1 over R2 equal to 4 multiplied with 3 plus 6 multiplied with 1 over 15. And if we solve this, we will have C1 over R2 equal to 6 over 5, which is equal to 1.2. And in this way, we are now done with the calculation of all the 4 possible transfer functions. Now, I want you all to go through this problem one more time. And with this problem, we are now done with the solved problems based on signal flow graphs. In the next lecture, we will discuss the limitations of Mason's gain rule. As of now, we are done with this lecture. Thank you for watching this lecture. I'll end this one here. See you in the next lecture.